the solution exists and it's unique. And when we get a positive answer from there, we can just shift everything. So we know that this is true for a general point. Okay, so that's going to be the theorem. So let's say C is a closed convex set of X. Then there exists a unique X0 from C such that the X0 minus X is actually just the infimum for Y minus X, where Y is from C. Okay. Oh, sorry. So X is 0 right now. So let's say just consider a simple case and know that there exists X0 such that this is just the infimum of Y, where Y is from C. Okay. So let's see the proof. So let's define D to be the infimum of Y and C. Then I know there exists xk in C such that the distance between, or the norm of xk is greater than or equal to D and less than D plus 1 over k. Now why is that? That's because of infimum in our definition for D, right? So with D is infimum, that means for any epsilon I can find something so that is between D and D plus epsilon, and that D epsilon is my 1 over k now. Right, so for any k I can do this. Okay, now I'm going to show that this xk forms a Cauchy sequence. And to show that, let's look at the say xk and xj. Okay, so the xk minus xj squared. Remember that by the parallelogram identity, we know this is equal to 2 times xk squared plus 2 times, I put 2 outside, xj squared minus the xk plus xj squared, right? And then we know that this is first term is less than D plus 1 over k. So and let me just keep writing this as one more thing to modify. So this is when I multiply 2, I divide 2 inside and I need to multiply 4 outside. This is xk plus xj over 2 squared. And why I'm doing this, or I can see that this term will be in C because C is convex. So since xk and xj are in C, so this is like a convex combination of them. It's actually the middle point between them. It's still in C since C is convex. So I have this. Well, I know that this first term here is less than D plus over k, actually squared. The second term is less than D plus 1 over j squared. Okay, let's say that j is bigger than k. Then I know this is less than or equal to 2 times D plus k over k squared plus D plus 1 over j squared. On the other hand, I know that this one is in C, so that's why this norm must be greater than or equal to D squared. And since it's subtracting it, so it's less than or equal to 4D squared. Okay, and then we can see that, for example, this j, since it's bigger than k, so this whole thing here is less than, this whole thing here will be less than or equal to d plus over k squared, right? Since j is bigger than k. So this is just less than 4 times d plus k over k squared minus 4d squared. And then the things become easy, right? This is just 4 times 1 over k, right, times d 2d plus k 1 over k. Okay, d is a fixed number, so you know that when k goes to infinity, this one goes to 0. And it's independent of j, so that means for any j bigger than k, as long as k is sufficiently large, this thing is approaching to 0, and that means this xk is a Cauchy sequence. Well, if this is Cauchy, we know that, so there exists some x naught such that xk converges to x naught. And this is the x naught I'm looking for, right? Because xk goes to x naught, and then I know that the norm of xk must also go to the norm of x naught, but this one is bounded by 1 over d plus 1 over k. Okay, as k goes to infinity, I know that this approaches to d, so this one has to be less than or equal to d. But on the other hand, this x naught is in C, because C is closed. So C is closed in a Hilbert space. X naught is in C, so this means that this one is also greater than d since it's in C. So on one hand, it is less than or equal to d, since this is true as k goes to infinity. And on the other hand, this is greater than or equal to d since x naught is in C. So this just means that x naught is in D, and this x naught itself is from C. Okay, so that proves that this x naught exists, and to prove it's unique is also pretty easy, as we know that if both x naught and x naught prime they're the projection, then they both have the norm d. They both have the norm d, right? And from here you can see that x naught minus x naught prime square, according to parallelism inequality identity, we have this square plus this square minus x naught plus x naught prime square. Okay. And what we know about this is similar as before. This is just divided by 2, and there is 4 outside. So this, since it's still in C, I know that this is less than or equal to d squared. Sorry, greater than or equal to d squared. Okay, and these two things are both d. So this is d squared, this is d squared. So altogether, we know that this is less than or equal to 0. Well, if it's less than 0, but on the other hand, this is greater than or equal to 0. So this means x naught is just x naught prime. And that explains why we can only have a unique projection of x, a unique projection of 0 onto this C. Okay? And then once we have that, it's pretty easy to show that when we shift this, then we shift 0 to some arbitrary point x, then we can still show that the projection is unique, exists and is unique. Okay? So this shows that if C is closed convex in X, which is a Hilbert space, then for any X of space X, there exists a unique X naught such that you can x0 in C such that x0 minus x is the infimum of y minus x, or y is from the convex set C. Okay, simply shifts everything from 0. Shift everything by distance x, then we'll get this correlate from the previous one. Okay, next we can consider so we know that the projection exists and is unique. Is there any way to characterize what is the projection point is? Not just that it is achieving the minimum value of the distance, but there will be some other properties that I can use to characterize this x. So this is all this is new for Hilbert space because we have the inner product structure. Then this is given by the following theorem. So it says that if I have a convex closed convex set, in the Hilbert space X, suppose we have that, then let's say that I have a for any x in the space X, the x0 is a projection of x onto C, and this means that the norm of x minus x0 is equal to the infimum of the y minus x0, as we said, right? If and only if x0 is a projection point, if and only if the real part of any y, sorry, say any y minus x and x0 minus x, let's say this must be greater than or equal to 0 for any y in C. Okay, so this is a sufficient and necessary condition for x being or x0 being a projection of x onto C. Okay, this must be true. Okay, so let's show why this is the case. For any y in C, let's consider this function phi y. Okay, phi y is going to be a mapping from the 0, 1 to R. Okay, and what this phi y is, it is defined as function of it's a function of t, where t is a number between 0 and 1, and this is y x minus t y plus 1 minus t x0 squared. Okay, remember that. So this is a C. This is the x0. Sorry, this is the x, and the projection is this is x0 here. Okay, and then you have a y. The y is some arbitrary point in C. Then for every given y in C, I'm going to define this phi y of t as x minus the convex combination between x naught and x and y. Okay, and you can observe several things. One thing is that when t is equal to 0, then this is gone, and this is just 1. So you just have x minus x naught squared. Okay. So you know this is the what do I say? This is the smaller than or equal to the x minus z, because this thing is in C. So this is less than or equal to z, x minus z for any z in C, right? That's one thing. We'll show that soon later. But once we have the phi y here, we can see that it's the function of t, and we know that the x naught is a projection of x onto C. So if and only if this phi y of t is greater than or equal to 0 for any t in 0, 1, and any y in C. The reason is, as you can see actually from the picture, well, this means that on the line segment between x naught and y, all the distance between this and the x is greater than or equal to the distance between x and x naught, and this y is arbitrary, so you can put the y to any other places. So by choosing different y's and different t's, if this phi y of 0 is always less than phi y of t for any y and any t, then it just means that x naught is a projection point. Okay, and we know that it's unique as well from the previous result. Okay, so we know that. And the question is, if the x naught is a projection point, if and only if this is true. So to show that, we just need to show that this is less than equal to, or sorry, as I said earlier, this is less than equal to the phi y of t for any t and for any y. This is equivalent to that. Okay, so let's see why this is the case. You consider the phi y prime. This is the function of t only, so we can actually take the derivative with respect to t, and what we'll get here from here is 2 times inner product of x minus ty plus 1 minus t x naught, and then we take the inner product with respect to t, we'll get, I think, x naught minus y. Okay, so if I take t derivative with respect to t one more time, okay, so how I got this? I just break this square. It's just the inner product of something times something, and there's t involved. So I can take the derivative with respect to t one more time, with respect to t, and the similar thing here. So when I take the derivative, I will get this 2, and then I'll have the y, x naught minus y. Sorry, here, x naught minus y again. So this whole thing will be just x naught minus y squared. Okay, and that is greater than or equal to 0. So now that I know that y if x naught is a projection point, if and only if this phi y 0 is less than or equal to phi y of t for any t between 0 and 1, and the y in the C, this will be equivalent to saying that x minus x naught is equal to the infimum for y minus x naught x. Y is from C. So these two are equivalent. Now this here, since I know that the phi y prime double prime is greater than or equal to 0, so that means it's a convex function in T. Okay, and then you have this right here. It's like I have 0, 1, so in T. I have a convex function between over this 0, 1 interval, and this point has the minimum value if and only if you see the it must be going up, right? Because it's a convex function, this must be going up, and you basically have this. So that means that the derivative here must be positive. Well, it's a non-negative at least. It's non-negative. So what is the derivative here? The derivative here is like the phi y prime at 0. But we said the phi y prime of t is that. So when we plug in t equals 0, we'll have 2 times. Sorry. So this is for real case. Let me just consider the real case first. So in this case, when t equals to 0, I will have just x minus x naught, x naught minus y. I'll have this greater than or equal to 0. Okay, sorry, I should have this as y minus x naught. Y minus x naught. I think, yeah. Y minus x naught. Yeah, should have that. So we'll have this greater than or equal to 0. So this is if it's real, then I don't really have this real part. I know that taking the interval of this will be this. But if it's not real, when I expand this thing here, I'll have this. So let me write it here. So I have x square minus x, and then this ty plus 1 minus t x naught. And I also have ty minus plus 1 minus t x naught, x plus no, I should do this in this way. So let me rewrite here. X minus 1 minus t x, this is the y plus t x naught, right? So let's rewrite this. This becomes x minus y plus t of x naught minus y. That should be that. Sorry. Okay, I'll rewrite that as x minus x naught plus t times x naught minus y, this square. Then I can break this square. I'll have x minus x naught plus t x naught minus y. And also repeat it. I have this, right? And then we can see that it just becomes that. And then I have the I have the t times x naught minus y, and x minus x naught, and also have t times not this t, but yeah, this will be the same t, but I have to take the t bar and x naught minus y, sorry, x minus x naught, and then x naught minus y. Okay, you just conjugate over the previous one, and then what I get, this is plus t squared x naught minus y squared. Okay, by the way, t is real value, so this is just t itself. It's just t itself. But this one, they are conjugate to each other. So when I add them up, I will just have the real part of them, right? 2 times the real part of them. So this is why it's 2t times the real part of the x naught minus y, x minus x naught. And then I have the t squared. It's a real number between 0 and 1. So x naught minus y squared. And then I have x minus x naught, which is also a real number, but it's a constant here. So I have a quadratic function of y, of t, then you have, we'll take the derivative of y with respect to t, you just get 2 times the real part of this plus 2t times x naught minus y squared, right? And then when t equals to then you can take the derivative with the t one more time, which is this. Okay, so that's why this is a convex. But also, when t equals 0, we can see that this prime at 0 is 2 times the real of that. And we just saw that this has to be greater than or equal to 0 as we're pointing to this point. It should be greater than or equal to 0. That's why this is greater than or equal to 0. Okay, so this is the sufficient and necessary condition for the x naught being a projection point of x. Okay, so that is for general convex, closed convex set. A particular type of closed convex set is a linear space, a linear subspace, or a linear manifold. So we can also consider the projection of M of some point x onto a linear manifold. So that's given by a corollary. A linear manifold is just a special type of closed convex set. So let X be a linear manifold of X, which is a Hilbert space. And then for any, say, X in outside of this M, we can consider the projection. So for any X in here, X naught, let X naught be the projection of X onto M. Then we can have the similar thing as before, right? We'll have, we should have this thing, but I'm going to make it, but this is going to be equal to 0. I'll show the reason why. So this X is a projection, so I should say this. X is a projection of X onto M if and only if you take the inner product of the, say, still y minus x naught. Yeah, y minus x naught, and x minus x naught, or x naught minus x. Let's see, anyway, this I'll show that this is equal to 0 for any y in M. Okay, so why that's true? On the one hand, we actually have this is greater than equal to 0, as we showed from the previous one, right? So we know that this, if it's projection onto M, then I will know that this is greater than equal to 0. But since I can choose it's a projection of X onto M, I know that this is it if and only if dy minus x naught, x minus x naught is greater than or equal to 0. The real part of this is greater than or equal to 0 for any y in M. This is from the previous theorem. But on the other hand, I can see that by choosing y prime to be negative, say I choose y prime such that the y prime minus x naught is equal to negative for y minus x naught. Let's say if this is the case, then the y prime is just x naught minus y minus x naught. But this is still in M. Since this x naught is in M, y is in M, so this is a linear combination of them, it's still in M. But by choosing this y prime, we'll be able to see that we know this real part of this y prime, x minus naught, x minus x naught. This is also in M, so that means this is also greater than or equal to 0. But on the other hand, we know the y prime minus x naught here is equal to the negative of y minus x naught. So that means the negative y minus x naught, x minus x naught, you take the real part of this, is also greater than or equal to 0. So that means if we remove this, this should be less than or equal to 0. So we just show that this is greater than or equal to 0, but on the other hand, we show that it's less than or equal to 0, and that means the real part of this is just equal to 0. Okay, and similarly, we can show that the imaginary part of this is equal to 0 by choosing, say, this is equal to I times that. Okay, and you can easily show that this just means that y minus x naught and x minus x naught, this is just equal to 0 for any y in M. Okay, so that's for linear manifold, the result actually can be even stronger. Okay, and they actually that's the corollary here. And I think the one last thing we want to show in this chapter is that when we have a linear subspace, so let's say I have a linear subspace M, so linear subspace of X, and then we can consider M and its orthogonal space. So what this means is, remember that this denotes all the x in X such that X is perpendicular to Y for any Y in M. Okay? And then we can show that for any, if we have this structure, inner product structure, then for any x in X, there exists a y in M, also z in M prime, and they're actually unique y, unique z, such that x equals to y plus z. Right? This is like the direct, x is a direct sum of M and M prime, M perp. Okay. So how do we get this? This is actually easy. You just have x. You do a projection of x onto this M, and that's how you get this unique y. And then take the difference between x and y, and then you get the z, which is also unique since y is unique. So you have that. Okay. You actually get this y and z in that way. Okay. And yeah, I think that's a like a direct sum structure in a Hilbert space. So this is all due to the inner product structure we have for inner product spaces, and we can consider bases, orthogonality, and from this line, going along this line, there are also many other advanced classes or research direction that concern about the structure of Hilbert space, constructing bases for that, and maybe doing some kind of computation or optimization over the space, Hilbert space. And but for this class, up to this point, we know the basics about all the Hilbert space, and this actually is an extension of the not only just the Euclidean space, but also the L2 space we learned. And we know that L2 space, it will be a general, it will be considered special case of or special example of Hilbert space. And this also has many applications in partial differential equations. Okay, now we start to learn more about the linear operator and the linear functional. So we actually have seen that before. We have considering homomorphism between Banach space or Hilbert space. So those operators or functionals, they're actually linear. And in this chapter, we're going to dig out more of the properties of these linear operators. Okay, so the motivation is actually very straightforward. We have seen lots of linear operations, especially in algebra, and for linear operations or linear operators, the most obvious property is that when you have a mapping, say T from X to Y, and X and Y are linear spaces, then we have, say, map everything in X to something in Y. So the linearity is about the combination of this X. Say we have alpha 1 x1 plus alpha 2 x2, right? And you apply T. If T is linear, then this must be equal to alpha 1 t x1 plus alpha 2 t x2. Okay, so that's what we call bilinear. And why this is common? The most common or the easiest example that we have learned in algebra is that when you consider a mapping from a linear transformation from say Rn to Rm, you just have to map every n-dimensional vector to some m-dimensional vector, and this mapping can be realized by a matrix, right? So we have x equals to x1 through xn, and then if you have a matrix, say we call A, the A is A11, A1n, and AM1, AMN, then you know that when you multiply x by A, then the AX will be a vector in Rm. So the T could be realized by some matrix A like this. Okay, so that's the basic example. And also derivatives, especially partial derivatives, they can be considered as a linear transformation as well. For example, if you have function f in from mapping from omega to R, and this omega is open set, then you can consider so this open subset of say Rn, then you can consider the partial derivative of this f. Say I have a partial derivative of f. This alpha is a multi-index, right? Alpha is like alpha 1 through alpha n, and then maybe the sum of alpha I for I from 1 to n. This is equal to some k. This is the order of the derivative. Then this operation here is linear. The reason is when you apply this, say, AF plus BG, this is the same, where A and B are real numbers, F and G are C infinity omega. So when I read this, usually it means this just this function is continuous up to the boundary, and also it's infinitely times differentiable. This is smooth. In some way, some text part is smooth. So in this case, we have A times the partial derivative of F plus B times the partial derivative of G. Okay, so it's like that. This is linear operator, and also integration is a linear operator. For example, when we consider the integration of F, especially like this, say we have a kernel function K that is from, say, R it's from Rn by Rn to R, then and let's say that K is continuous. Okay. And then we can define the ik of u to be where this u is from the C, say C omega. Then we can consider the integration of u using this kernel function, or in other words, we can consider the convolution of this kernel function and this u. Right? We can consider this, and then this is also a linear operator in this space. The reason is we can consider ik of au plus bv, right? Then you can easily see that this is just a times iku plus b times ikv. Okay, there are lots of examples that are linear, although it's very special, very strong condition about linearity, but it actually appears a lot in practice, in algebra and also in analysis. Okay, so formally what's the definition for linear algebra? Linear transformation is that our linear operator is that we have two linear spaces D a linear subspace of X. Then, so this is the you can just consider X as the domain, but let's be more specific. They say that T is only a mapping from a sublinear space of X, which is called D here, to Y, and it's not necessary to fill in all the entire Y, but maybe a subset of Y. So this D, this T is called a linear operator if, as we said earlier, if you have, say, alpha x plus alpha prime, this is equal to alpha tx plus alpha prime tx prime. We sometimes put parentheses, sometimes not. Usually, we don't need to put as long as it's clear. I think it's easier to just put tx without parentheses. Looks cleaner. But anyway, if this is true for any alpha prime in R or in C, it depends on which the linear space is in R or in C. And also x prime in D. Okay. In this case, the D is called the domain of T, and it's called domain of T, and the TD is called the range of T. Okay, or sometimes you can call it the image of D under the linear operator T. Okay, so that's the definition. But as we mentioned earlier, there are many concrete examples for this. For example, you can consider matrices, you can consider partial derivatives, you can even consider a combination of a linear combination of partial derivatives. For example, say I have a mapping from just this. Then you can consider T to be, say, the sum of sigma alpha d alpha. Alpha is less than or equal to k. So alpha is a multi-index. So here again, this omega is open stat in Rn, and this alpha is equal to alpha 1 to alpha n, and it's a multi-index. So every one of them is an integer, is a natural number or 0, and the sum is less than or the sum is less than or equal to k. This sigma alpha indicates the coefficient for the let's say for this operator, and this d alpha takes the alpha partial derivative of the argument. For example, if I take the t on x, the x is in C omega, then this is just the sum of sigma alpha partial alpha x. Maybe let's use another notation, maybe it's more clear. So I have f in here, I can consider this. Okay, also this is f. Okay, and alpha is less than or equal to k. And even this is dependent on x, since it's f as argument x. Consider this. If we consider this at every point x in omega, this is just a partial derivative of f at the point x. And this one can also be dependent on x. Okay, it's okay for depending on the specific points because this is still a linear operator. As you can see, if I take t of alpha f plus beta g, it is still equal to t, alpha times tf plus beta times tg. Okay. So after mapping t, you get a new function, new continuous function in here, and that is this. Okay, so that's another example. So it's also linear. This is actually how we define, for example, linear partial differential equations. If the derivatives applied or the partial derivatives applied to a function is a linear operator like this t, which is written in this way. As we said, this could be dependent on x. Could be dependent on x, then this will be a linear operator. So, for example, you know Laplacian operator. So what is the definition for that is, say I have x, okay, I say x, y is in C omega, it's equal to C omega, and then again this omega is open, let's say open bounded set in Rn. Doesn't have to be bounded, I just want to specify that we have a PDE defined on a bounded domain. Then say the u is in x, and then the du is a partial derivatives, which is the du dx1 all the way to du dxn, because right now every x is an n-dimensional vector. Okay, so it's in Rn, and the divergence of a vector. Say I have a vector, I call it f. So you know that f is a mapping from omega to n-dimensional vector. Okay, so what that does is you have this f, f of x. It is actually f1 of x all the way to fn of x. You see in Cn. Okay, and the divergence of this f is actually the partial derivative of f1 with respect to x1 plus partial derivative of f2 with respect to x2 all the way to partial derivative of fn divided by dn. Okay, so that's the definition for divergence. then the combination of the two, a composition of the two, you take the partial derivative, you take the gradient of u, you get a vector, and you take this divergence of this vector again. Then as you can see, this is f1 now, right? And then you take the partial derivative of this f1 with respect to x1. So you just take the partial derivative with respect to x1 twice for u. So you have d squared du d x1 squared. Okay, so you take the partial derivative with respect to x1 for twice. And similar for others. So all the way you have that. Okay, so that's called the Laplacian of u at the point x. Okay, and this can also be treated as the Hessian of u, the trace of the Hessian, because the trace of the Hessian, usually Hessian is written as h of u, or this one is actually the d squared u somehow. It means that you get a Hessian matrix and take the trace, which is the sum of the diagonal entries. You have Laplacian u. Okay, so that's a linear operator. As you can see, the Laplace of au plus bv is just the a Laplace u plus b Laplace v, because all these operators are linear. Okay, they're linear operators. So you eventually get a composition of linear operators. You get a linear operator in the end. Okay, and not only that, you can even extend this. For example, I have, you can consider this. Say you have the divergence. By the way, divergence sometimes is written as this. Okay, and the gradient is sometimes just written as this. So let's say this is the gradient of u, and this is the divergence of f. Okay, the divergence of say gamma du. So this is also come as the extension of the Laplacian. So what this one is, it is the divergence of this gamma function, which is dependent on x. And the du, remember that this is the partial u partial x1 all the way to partial u partial xn. Okay, and every one of them is a function of x. Okay, each one of them is a scalar valued, and there are functions of x. And then after you multiply this inside to each one, you get a vector, and you can take a divergence one more time. Okay, so that is another example. And actually, in this case, you can show that this is just equal to the inner product, or the dot. This is sometimes called dot product, plus the gamma Laplace u. Okay, and this is you get a scalar at every point x, and the meaning of that is at every point x, you have the d gamma, which is a vector, n-dimensional vector, and this is also n-dimensional vector, so they're all n-dimensional vector. And then this is scalar for every fixed x. This is a scalar, and this is also a scalar as we showed before. So eventually you just get a scalar. So that's the meaning. Okay, so all of these operators are linear. Okay, even if this gamma depends on x. The key is that it doesn't depend on u, only depends on x. So as long as that's true, then you have a linear operator. Okay, I think there are several other examples on the notes. Let me see if there are some more notable ones. So, for example, yeah, why we specify that D is a domain. So, for example, if you consider T is the partial derivative, where T is our partial derivative, then you can consider the mapping from L2 omega to L2 omega. But actually, you know that you cannot really take a derivative to any function in L2. You can only apply that to a subspace of L2, which is, say, if you just have a partial, say partial 1, instead take the partial derivative with respect to x1, then you can work on C1 space. So for example, for all the continuously differentiable function, consider this, then you can see our T is mapping from that to some subspace of L2. So this is like the D, this is like the X, okay? So like the Y, this is like the D here. Okay? So your T, when you define a T, you know that it may not be able to apply to every point in X, and then you just restrict yourself to the domain where you can actually apply this. Okay, so that's another example, and linear functional. So linear functional is actually just a linear operator, but the Y is a field, it's number fields such as R or C. So T is called a linear operator. So again, the T is a linear transformation. It's from X to Y. It's also called operator. Called functional. Specifically, if this Y is just R or C. Okay, so in this case, T maps any vector in X to a scalar. Okay, so in this case, we call it a linear functional. So just a special type of linear operator. Okay, so that's linear. And also say this is we consider integration. Suppose we define, say I have X to be the C omega, and I can define the mapping T from X to R, which is defined as for any function f in the space X, I map it to Tf, which is by definition the integral of f over this set omega. Okay. Now you can see that for any f, it is mapped to a number on the right side. Right? So the T is a linear functional. And this linear is obvious, right? So it's a linear operator, but it's mapped to R here, so that's why it's called a linear functional. So that's a linear functional. But if you have this f, then you map this f to, say, fx squared dx, then this is not linear anymore, right? Because it doesn't satisfy this. Doesn't satisfy this thing, right? So you don't really have equality for this one. So this is not true. That's why it's not a linear operator. Okay, so this is not linear functional. Okay, so yeah, I think this is quite a set of examples. In practice, you need to recognize which kind of function is a linear, which is not. Although it's pretty special, but we even have seen some nonlinear operators before. Like we consider fixed point theorems. Those operators are not necessarily linear. Actually, they must not be linear. But the linear operators they do have their use. And because it's linear, we can derive lots of very useful properties. And especially when we consider the dual spaces, most of the operators are considered as linear operators. So we'll see that later. And that's why we spend such a long time. We will spend quite a bit of time on the linear operators. And this is the major part in linear functional analysis. Okay. So now, as we said before, the linearity is most about the algebraic structure. Once we have linear spaces, we can consider linear operators linear functionals. But what makes this functional analysis more interesting is that we have the linear vector spaces, or normed vector spaces, or normed linear spaces. That's the same thing. For this kind of spaces, we don't just have algebraic structure, but also have topological structure induced by the metric or by the norms. So we're going to also need to see how these linear operators behave under such situation. So we say we have x and y that are not just linear spaces, but they're normal linear spaces. Then do we get something else? So that's the major topic in this chapter. We're going to start with continuity. So let's say we have x and y, which are both B-star spaces, which are linear normed vector space or normed linear space. And we have a D, which is a sublinear space or linear subspace. Linear subspace. And we have the dt, which is a mapping from D to Y, that is a linear operator. And we call the T continuous if the txk converge to tx. Now remember that both of them are in the space Y. Okay, if this is true whenever the xk converge to x. Okay, so as long as in the space X, you have a sequence xk that converge to x, then after the linear operator, you map everything to the space Y. And txk is a sequence in Y. Tx is a point in Y. If this also converges to that, then we call this T continuous, right? If this is true for any such sequence. Okay, so that's the continuity. So this it's which is the continuity we have all the time, right? That's the how we count the continuous function. But if t is linear, we actually can make this much simpler, because if it's linear, then we can basically shift everything to 0. For example, I can shift, instead of xk goes to x, I can just say that xk minus x goes to 0. Right? It's the same thing. Then on the other side, we'll just have a t of sk minus t of x goes to 0. But this one is just a t of xk minus x, because t is linear. So what it turns out that when we consider linearity, we consider continuity of a linear operator, we just need to care what happens near 0. Because if it's non-zero, then we can just shift everything back to 0. This is the linear space and t is linear. Okay, and that's why we have this very important, simple but very important property. The function t, or the operator t, let's say t is a linear operator, then t is continuous in the space X, which is the case here. Definition here, whenever, no matter what this X is, as long as xk convert to x, you have that. This is actually equivalent to saying that t is continuous at the point 0. Okay, so yeah, that's why you can see it's a really strong one that is equivalent to something that is much easier to check. Right? So apparently this direction is true. If it's continuous everywhere, it must be continuous at 0. But this direction, this is just because the thing I mentioned. If you have if t is continuous at 0, that means t of xk minus x will converge to 0 whenever xk minus x goes to 0. Right? Because this goes to 0 means that you have this, and this goes to 0. That means the t is continuous. This is because t is continuous at the point 0. But this whole thing here is equal to txk minus tx, and this is just xk goes to x. Okay, so that's why that we only need to consider the continuity of t at the point 0. As long as it's continuous there, then it's continuous everywhere. Okay, so that's continuity. It's pretty simple. I just need to check this. Just check this. Okay, bounded operators. So we say the operator is bounded. So let's say x and y be B star space. And again, the D is a linear subspace. And then T is a linear operator. Then we say T is called bounded if there exists some m such that the norm of x, tx, apparently this is norm in the space y. Okay, is less than or equal to m times the norm of x. If this is true, then we say that T is bounded. Okay, if this is true for any x, we say T is bounded. Well, you can see we actually have a equivalency between the continuity and the boundedness. It's all because it's a linear space. It is a linear operator. So let's say that again, x and y are B star spaces, and the T is a linear mapping or linear operator. Then the T is continuous if and only if T is bounded. Okay, and I also said that T is continuous if and only if it's continuous at point 0. Okay, but this is establish a equivalency between continuity and boundedness. They are actually the same thing for continuous for linear operators. Why is that? So on the one side, if you know it's bounded, then suppose T is bounded, then we know that when xk minus x goes to 0, this implies that T of xk minus x, which is equal to, so on the one hand, this is equal to txk minus tx, since T is linear. But on the other hand, this we know it is less than or equal to, on the other hand, I know that this is less than or equal to m times xk minus x. But if this goes to 0, this should be going to 0. So that's why this is going to 0, and that means this one goes to 0, which means that txk goes to tx. Okay, so if this tells us that the T is continuous. The other direction, suppose it is continuous, we want to show that T is bounded. Well, if not, that means we cannot find such an m, so that this is always less than or equal to m. So that means for any k in the integer, as an integer, there exists some xk such that the txk is bigger than or equal to k times xk, right? If this doesn't, if you don't have such an m to make this happen for all k, then that for all x, that just means that for every m, for every positive number m, or so let's say any number k, we have this bigger than or equal to k. Okay, there exists some xk, so that this is bigger than or equal to that. Okay, so now when we have this, we can consider, say, this, we can define or denote the yk. So apparently the xk cannot be 0, because if xk is 0, t is linear, then this must be txk must be 0. sorry, it should be bigger than, right? Then this cannot happen because on the right hand side we know this is bigger than or equal to 0, and on the left hand side you cannot really have this equal to 0. So the xk must be non-zero in this case. So we can consider xk over k times xk. And now you can see, not called yk. Yk seems to be from y space because it's actually still from x space. Let's call it xk prime, or let's say xk hat. Okay. So let's denote this. And now you can notice that the norm of xk hat, which is still in x, right? And this is just equal to the norm of xk over k times the norm of xk, but this is just cancelled out, so I have 1 over k. So I notice that xk hat has a norm equal to 1 over k, and that's supposed to go to 0, which means that my xk hat goes to 0. But on the other hand, let's see the txk hat. Txk hat, according to what I have here, it is just equal to t of xk over kxk. But the k times the norm of xk, this is this number on the denominator just a scalar. I can pull it out. So I have a kxk and then txk. Okay, and according to our assumption here, for a definition for xk, this is bigger than 1. Okay, now what we have is that the xk hat, as a sequence, they convert to 0 in space x. But txk hat, as a sequence in y, their norm is always greater than or equal to 1. That means it's not converging to 0. And this is a contradiction to the continuity of t at 0, or continuity in the whole space, since it's equivalent. So that's where the contradiction is. Contradicts to t being continuous. That's where the contradiction comes from. So that means if t is continuous, it must be bounded as well.